To the 2017 midterm exam, the last question, question 5, which is to identify communication systems from the table provided that is band limited. And you have to justify your choice. And that's to explain the qualities of a band limited system and suggest an appropriate modulation format. And then you're supposed to do the exact same thing, but in this case for a power limited signal. And actually there's many choices here that are available. So we have, in fact, 6 different systems which are being described. In this case, there's not really anything in the notes that are going to help you, other than the spectral efficiency plane. So I did take out the spectral efficiency plane to help in our discussion. So we have let's see what we got here. We've got 1, 2, 3, 4, 5, 6 possibilities, and we have to pick out 2 of them. We have to find one that's band limited and one that's power limited. Band limited, how are we going to know if it's band limited? Well, what are we given as information? We're given the amount of bandwidth available, we're given the required bit rate, and then in addition to that we have what kind of power it uses and the signal strength, typical signal strength. So we can imagine that the bandwidth column is going to help tell us if it's band limited, and that the signal strength column is going to help tell us about whether it's power limited. But you have to be careful because it's not the absolute bandwidth that really matters. What matters is the relative bandwidth to bit rate, because you want to have enough bandwidth available for you to send the data rate that you want to send. So let's do something where we put bit rate, which is of course RB, and we'll call bandwidth BW. And we're going to do something that looks like spectral efficiency. What's spectral efficiency? I guess that was in the notes. That would be RB over the bandwidth. So we're going to create a column here, which is about the ratio between the bit rate and the bandwidth. And so here we have something like 3.3 because it's 10 divided by 3. I need 10 kilobits per second. I have 3 kilohertz. And in the next one we have a car door opener. And in this case it's something like 10 bits divided by 20 times 10 to the 6th. So we're looking at something like 5 times 10 to the minus 7, something really small. Does that make sense? Sure, it makes sense because I'm opening a car door. I'm not sending much data. I'm sending like the code for this is my car. And then I'm using one of the available bands, and the available band happens to be pretty wide. Maybe I'm using the same band as a Wi-Fi signal. So it's not at all surprising. This would require, like no spectral efficiency. Really, really small is good enough. And the next time we're going to look at something like a microwave link. So they've paid to have 30 megahertz of frequency blocked off for the dedicated link. And they're trying to send a good data rate through that. So we've got 100 megabits per second divided by 30. So we're getting something like 3.3 again, bits per second per hertz. And we're looking at the Mars lander. Oh, this is interesting. So Mars lander, I can get to have a lot of bandwidth because let's face it, on Mars there aren't too many cellular telephone systems. So I can have a whole lot of bandwidth, 4 gigahertz, but I only need a small amount of data because I'm sending data all night long, and I'm not collecting that much data, and so this would probably be good enough, and this comes to 5 times 10 to the minus 6. So this is another example where spectral efficiency is just not very important. The next example is cellular data. Okay, now this is where I've only got like 100 kilohertz, so I'm paying like really, really expensive for this bandwidth, and I'm trying to send, I'm sorry, I got that inverted. I'm trying to send 1 megabit per second. I'm trying to give good service to my clients, but I want to divide that by 100 kilohertz. And so this is coming out to be something like 10 bits per second per hertz. So very demanding because I have to pay so much for my bandwidth. Next would be the cable internet. And so this would be like having a cable like Videotron coming to your house. And in this case, we're looking at 50 megabits per second. And got 10 megahertz available on my coaxial cable. So I'm getting 5 bits per second per hertz. So this is what is going to determine for us whether or not it's band limited. For instance, maybe the smallest band, one of the smallest bands I have is something like this 20 megahertz. So I only have 20 megahertz for my car opener, but I'm not band limited at all. Even I guess, I'm sorry, it's the kilohertz that were the smallest. But 20 megahertz falls in the middle somewhere. And still, we're able to, it's just not critical how much absolute bandwidth is available. What matters is the ratio. So once we have the efficiency, then we can sort of look at the bandwidth efficiency plane. And this is really what's going to tell us, is this band limited or power limited? So we know that if we're somewhere up here, this would be the band limited zone. And if we're somewhere down here, do it like this, I guess, this would be something like the power limited zone. So right away, if I come up with something that needs 3.3, so I'm looking, is it like greater than 1 or less than 1? And here we can see less than 1 are here. So these two are going to be the power limited, or they're not bandwidth limited. Let me put it that way. They're not bandwidth limited. And then all of these others are really bandwidth limited. So we could pick any, you only asked to explain for one. And let's take an example. So let's take the twisted pair and say, why is it bandwidth limited? I say, this is my example. Twisted pair is bandwidth limited. How do I know it's bandwidth limited? Because the ratio is 3.3, which is in the band limited range, which means that being efficient in spectrally efficient is important for the system because you're trying to put a fairly high bit rate through a fairly limited bandwidth. And then you would say for the power limited, you would say it's power limited. Why? And now what we're going to do is power limited. We're going to take another look at why we're going to call it power limited. And we're going to say it's running on battery and it's running on solar and it's probably pretty weak. So these are power limited because they're really, first of all, we'll say they are not band limited, but are they really power limited? And then we could go to the argument of what the power source is to give it. Now I'm going to take as an example for, not really a counter example, but I would say a poor choice for this one, and that would be cellular, because cellular is kind of both power and bandwidth limited. So it is definitely bandwidth limited, but it's really, you can make an argument that it's also power limited, that you just don't have much power. And that just means it's challenging. It's just like the fact that it falls in one corner of the bandwidth efficiency plane doesn't tell the whole story. So what's nice about the power limited systems is that you can get, really good efficiency, if I have the system like the Mars lander, I can still send a decent amount of data because I just use a whole lot of bandwidth. It just becomes really ineffective. So anyway, the last part, so what did we pick? So we picked here twisted pair, and we picked the car door. What did we pick? Well, we'll pick it now. So the twisted pair is our bandwidth limited, and the other is our power limited. and we gave our reasons. Bandwidth limited because, the efficiency has to be greater than 1. I have to put a lot of information into a constrained bandwidth. And the power limit is because the opposite is true. I have all kinds of bandwidth compared to what the data rate is required. And on top of it, I'm running on limited power supplies or weak signals. Then the next question is to propose a modulation scheme. And this is where we have to get a little more careful. So when I'm going to propose a modulation scheme, I have to take three, propose modulation scheme. I have to do three things. I've got to get the BER versus SNR, if you will, the power efficiency. I've got to do the spectral efficiency, and I've got to do the cost. All three has to make sense. Let's look, for instance, at this power limited system. And I chose the car door opener. Now, think about the car door opener. If I wanted to go with a solution at m = 4, that would be 1, and the other extreme would be 4096. And you have to ask yourself, when I'm looking at the complexity side, the cost side, which is going to be more expensive? And I think it's pretty intuitive that having 4,000 symbols in the constellation is going to be a bit more pricey, whereas only having a few, you wouldn't be expensive at all. In fact, you could just do binary. Probably BFSK would be good enough, and that would be the cheapest way. So because I chose car door opener, I'm going to propose something like BFSK as something, or maybe 4FSK because maybe it's a little more power efficient, but it's not terribly important, and it's cheap. Now, if I was going to go for the Mars lander, suppose I had chosen that to be my solution. In that case, I might say, no, I'm going to go with the 4,000 one. Why? Because I need a lot less EB over N0. And because I want to talk to Mars, it's pretty far away, and I'm going to have a very weak signal, then it would probably be okay. And it'll cost more, for sure it'll cost more, but I can tolerate it. I'm only sending one probe to Mars, two probes to Mars. So that would be a suggestion for the power limit. And now let's look at the bandwidth limited. And now I need something like 3.3. So I'm going to look at my solutions and say, well, it's got to be above 3.3. It's got to be somewhere above here because I need that much. And so I could look at something like 16 QAM, or I could pick 16 PSK. But of course, QAM is more BER efficient. And they're both pretty similar in cost. Maybe PSK is a little bit cheaper, but not terribly much. Pretty much the same. And so I would probably say that for a twisted pair, I'd probably look at something like 16 QAM. Because 16 will give me 4 bits per second per hertz. Definitely meet the efficiency requirement. If you look at the solutions, you'll see some arguments, calculations for each one of these choices.